It's a pleasure to meet you, Dr. Einstein. I've always admired your work in physics.
Likewise, Mr. Tesla. Your contributions to the field of electrical engineering have been invaluable.
Thank you. I've always been fascinated by the fundamental nature of reality and the laws that govern it. Lately, I've been exploring the intersection of consciousness and quantum mechanics.
Ah, yes. The mind-boggling implications of quantum mechanics have been the subject of much debate and speculation. What is your take on it, Mr. Tesla?
I believe that the nature of reality is far more mysterious and complex than we can ever hope to fully understand. The quantum world in particular seems to defy our everyday intuitions about cause and effect.
I agree that the quantum world presents us with many puzzles. However, I still maintain that there is a fundamental reality underlying all physical phenomena, even if we can't directly observe it.
Perhaps. But I also think that consciousness plays a more fundamental role in shaping reality than we give it credit for. The observer effect, for example, suggests that the act of observation itself can affect the outcome of an experiment.
I understand your point, but I believe that there are underlying physical laws that determine the behavior of particles regardless of whether we observe them or not. The uncertainty principle, for example, tells us that we can never know the precise position and momentum of a particle at the same time, regardless of whether we observe it or not.
That's certainly true. But I still think that consciousness plays a role in shaping reality at a deeper level. After all, our own subjective experiences and perceptions shape our understanding of the world around us.
That's an interesting perspective, Mr. Tesla. It's certainly worth exploring further. However, I think we should also be careful not to let our philosophical musings overshadow the rigorous scientific investigation that is necessary to truly understand the nature of reality. So, Nikola, let's start with the basics. What is classical physics?
Classical physics is the branch of physics that deals with the behavior of macroscopic objects, such as planets, stars, and everyday objects.
That's right. It's the study of motion, forces, energy, and matter, and it's based on the laws of classical mechanics.
And those laws were established by great scientists like Galileo and Newton, who were among the pioneers of classical physics.
Exactly. They discovered that the motion of objects can be described by 3 laws of motion, which we now call Newton's laws.
And those laws describe how an object moves when a force is applied to it.
That's correct. They also discovered that the force of gravity affects the motion of objects, which led to the development of the laws of gravitation.
And those laws explained how planets move around the sun, which was a major breakthrough in our understanding of the universe.
Yes, and classical physics also includes the study of waves, such as light and sound waves.
That's right. The behavior of waves can be described by the laws of wave mechanics, which were established by scientists like Huygens and Fresnel.
And classical physics also includes the study of thermodynamics, which describes the behavior of heat and energy.
And it's the foundation for technologies like steam engines, which played a major role in the Industrial Revolution.
Exactly. Classical physics has been essential for the development of many technologies that have shaped the modern world.
And it's still relevant today, even with the emergence of quantum mechanics.
Yes, classical physics provides a solid foundation for understanding the physical world and remains an important part of our scientific understanding of the universe.
I couldn't agree more, my friend. Classical physics is a fascinating subject that has helped us to better understand the world around us.
While classical physics has been a major force in shaping our understanding of the physical world, it does have its limitations, especially when it comes to studying small objects.
That's right, Einstein. The laws of classical physics work well when studying macroscopic objects, but they break down when dealing with the incredibly small particles that make up matter.
Yes, classical physics cannot fully explain the behavior of particles such as electrons and photons. We need a new set of rules which we now call quantum mechanics to understand their behavior.
The failure of classical physics to explain the behavior of small objects is due in part to the fact that classical mechanics is based on the principle of determinism.
That's right. Determinism is the idea that the state of an object at any given time can be used to predict its state at any future time.
But with small particles, there is a fundamental limit to how precisely we can know their position and momentum at the same time. This is known as Heisenberg's uncertainty principle.
And this uncertainty principle means that we can't predict the future state of a particle with certainty, which contradicts the principle of determinism.
Another limitation of classical physics is that it assumes that the universe is continuous and infinitely divisible.
But the discovery of the discrete nature of energy, as described by Max Planck's theory of quantization, shows that the universe is not continuous at the microscopic level.
And this discontinuity of energy is at the heart of quantum mechanics, which is a fundamentally different way of describing the behavior of particles.
It's important to note, however, that classical physics is still useful in many applications, especially those involving large objects and slow speeds.
Absolutely. While it may have its limitations, classical physics is still a crucial part of our understanding of the physical world, and we can't discount its importance in shaping modern science and technology.
That's right, Nikola. And by understanding both classical and quantum mechanics, we can gain a deeper understanding of the universe and its behavior, from the smallest particles to the largest structures.
Speaking of quantum mechanics, Albert, can you give us a brief overview of how it developed?
Sure, Nikola. Quantum mechanics emerged in the early 20th century as scientists were trying to understand the behavior of subatomic particles, such as electrons and photons.
And who were some of the key figures in the development of quantum mechanics?
Well, there were many, but some of the most notable include Max Planck, who first introduced the concept of quantization in 1900, and Albert Einstein himself, who proposed the idea of the photoelectric effect in 1905.
And what is the photoelectric effect?
The photoelectric effect is the phenomenon where electrons are emitted from a material when light is shone on it. This helped establish the idea that light behaves as both a wave and a particle, which was a major breakthrough in quantum mechanics.
Fascinating. And what other discoveries helped establish the foundation of quantum mechanics?
Well, in 1925, Werner Heisenberg proposed the uncertainty principle, which states that it's impossible to know both the position and momentum of a particle with absolute certainty. And Erwin Schrödinger developed the wave equation, which describes the behavior of subatomic particles as waves.
So it sounds like the development of quantum mechanics was a major shift in our understanding of the behavior of particles at the subatomic level.
Yes, it was a completely new way of looking at the universe and challenged many of the fundamental concepts of classical physics.
And how has our understanding of quantum mechanics changed over time?
Well, there have been many advancements and discoveries in quantum mechanics since its initial development, such as the discovery of antimatter and the development of quantum field theory. But even today, there is still much we don't fully understand about the behavior of subatomic particles.
It's amazing how science is always evolving and uncovering new discoveries.
Indeed, Nikola. And by continuing to study both classical and quantum mechanics, we can gain a better understanding of the universe as a whole.
One of the most interesting aspects of quantum mechanics, in my opinion, is the idea that particles can exist in multiple states at once. Can you explain this concept a bit further, Albert?
Yes, certainly. One of the key principles of quantum mechanics is the superposition principle, which states that a particle can exist in multiple states or locations at the same time.
That's quite different from classical mechanics, where a particle is always in a specific location or state, right?
Exactly. In classical mechanics, we can always determine a particle's location and velocity with precision. But in quantum mechanics, the uncertainty principle means that we can only know the probability of a particle's location and velocity.
That's quite fascinating. And how does this superposition principle apply in practice?
Well, let's take the example of an electron. Normally, we would expect an electron to exist in a specific energy state, but with the superposition principle, we can imagine that the electron is simultaneously in multiple energy states at once.
I see. And how do we observe or measure this superposition of states?
That's a great question, Nikola. One way to do it is through a process called quantum entanglement, where two particles become correlated in a way that is not possible in classical mechanics. By observing the state of one particle, we can learn about the state of the other particle, even if they are separated by a great distance.
That sounds like a very promising area of research with a lot of potential applications.
Yes, it certainly is. From quantum computing to quantum cryptography, the principles of quantum mechanics have the potential to revolutionize many fields of science and technology.
One thing that has always fascinated me about quantum mechanics is its mathematical framework. Can you tell me more about the mathematics behind this field, Albert?
Yes, of course. Quantum mechanics uses a mathematical tool called wave functions to describe the state of a particle. The wave function gives us information about the particle's location, energy, and other properties.
And how do we use wave functions to make predictions about the behavior of particles?
That's where the Schrödinger equation comes in. It's a mathematical formula that allows us to predict how a particle's wave function will evolve over time, given a particular set of initial conditions.
I see. So the Schrödinger equation is like a recipe for predicting the behavior of particles.
Exactly. And by solving the Schrödinger equation for a given system, we can make predictions about everything from the probability of a particle being in a certain location to the energy levels of atoms and molecules.
That's quite fascinating. And what other mathematical tools are used in quantum mechanics?
Well, another important concept is the use of operators, which are mathematical tools that allow us to extract information from wave functions. For example, the position operator tells us the position of a particle, while the momentum operator tells us the momentum of a particle.
It sounds like the mathematics of quantum mechanics is quite complex. How do scientists use these tools to make predictions about the behavior of particles?
It's true that the mathematics can be quite challenging, but it's through these mathematical tools that we can make precise predictions about the behavior of subatomic particles. And by comparing these predictions to experimental results, we can test and refine our understanding of quantum mechanics.
The Schrödinger equation seems to be a central piece of the mathematical framework of quantum mechanics. Could you tell me more about it and how it allows us to predict the time evolution of quantum systems?
Certainly. The Schrödinger equation is a partial differential equation that describes how a quantum system evolves over time. It tells us how the wave function of a system changes in response to the energy of the system and the external forces acting on it.
And how does the equation actually work?
Well, the equation involves a quantity known as the Hamiltonian, which is a mathematical operator that describes the energy of a system. When we apply the Hamiltonian to the wave function of a system, we get a new wave function that describes the state of the system at a later time.
So the Schrödinger equation essentially tells us how the wave function of a system changes with time based on its initial conditions and the Hamiltonian of the system.
Exactly. And by solving the equation for a given system, we can make predictions about the future behavior of that system.
That sounds quite powerful, but how do we actually solve the equation for a given system and make those predictions?
Well, the Schrödinger equation is a differential equation, which means that we need to find a function that satisfies the equation. In practice, this often involves approximations and numerical methods to find solutions.
I see. And what kind of predictions can we make using the Schrödinger equation?
The Schrödinger equation allows us to predict the probability of a particle being in a certain location, as well as its energy levels and other properties. It's a fundamental tool for understanding the behavior of quantum systems, from subatomic particles to complex molecules.
You mentioned that the Schrödinger equation allows us to predict the probability of a particle being in a certain location or having certain properties. Could you explain how this works in more detail?
Sure. In quantum mechanics, we can't predict the precise position or velocity of a particle, but we can calculate the probability of finding it in a certain location or having a certain momentum. This is described by the particle's wave function, which gives the probability amplitude for a particle to be found in a particular state.
And how do we calculate the probability distribution for a particle's properties?
We use the wave function to calculate the probability density, which is the probability of finding the particle in a particular volume of space. The probability density is given by the square of the wave function, and it can be used to calculate the probability of finding the particle in any particular region of space.
So the probability density gives us the probability of finding the particle in any particular location. But what about other properties, like its momentum or energy?
For other properties, like momentum or energy, we use what's called an operator. An operator is a mathematical function that operates on the wave function to give the value of the property. For example, the momentum operator operates on the wave function to give the momentum of the particle.
And how do we use the wave function and operators to calculate the probability distribution for those properties?
We use the same approach as we did for position, but we calculate the probability density for the property in question. For example, the probability density for momentum tells us the probability of finding the particle with a particular momentum.
I see. So the wave function and operators allow us to calculate the probability distribution for any property of a particle. That's quite remarkable.
Yes, it's one of the key insights of quantum mechanics. and it's allowed us to make many predictions about the behavior of particles and systems at the quantum level.
I've heard that there are limitations to how accurately we can measure certain properties of particles. Can you explain that?
Yes, that's the uncertainty principle. It states that there is a fundamental limit to how precisely we can know both the position and momentum of a particle at the same time. The more precisely we measure one property, the less precisely we can measure the other.
That seems counterintuitive. Why can't we measure both properties with perfect accuracy?
It's because of the wave-particle duality of particles. The more accurately we measure a particle's position, the more its wave function collapses, and the less accurately we can determine its momentum. And vice versa, the more accurately we measure its momentum, the more uncertain its position becomes.
So this means that there are inherent limitations to what we can know about particles at the quantum level.
Yes, that's correct. And it has profound implications for the nature of reality and our ability to make predictions about the behavior of systems at the quantum level.
And does this uncertainty principle apply to all properties of particles or just position and momentum?
It applies to any pair of complementary properties, such as energy and time, or angular momentum and orientation. The more accurately we measure one property, the less accurately we can measure the other.
This uncertainty principle seems to limit our ability to make precise predictions about the behavior of particles and systems at the quantum level.
Yes, it does. And it also has practical implications for technologies that rely on quantum phenomena, such as quantum computing and quantum cryptography. We need to take into account these limitations when designing and building such devices.
So if I understand correctly, the act of measuring a particle's properties can affect its state and behavior?
Yes, that's right. In quantum mechanics, the act of measurement can actually change the state of the particle. This is known as the observer effect or measurement problem.
How does that work?
When we measure a particle's properties, we collapse its wave function. This means that the particle transitions from a superposition of possible states to a definite state.
So the act of measurement changes the probability distribution of the particle's properties?
Exactly. And that, in turn, affects how the particle behaves.
This seems to imply that our measurements can never be completely accurate since they affect the very thing we're trying to measure.
That's correct. The act of measurement is always an interaction between the observer and the observed system, and it always affects the system in some way.
So how do we deal with this problem in practical applications of quantum mechanics?
Well, we need to be very careful in designing experiments and making measurements. We need to minimize the disturbance caused by the measurement process, and we need to take into account the fact that our measurements may affect the system we're trying to study.
It seems like quantum mechanics introduces a lot of new challenges and limitations that we don't see in classical physics.
Yes, that's true. But it also opens up new possibilities and allows us to study and manipulate the quantum world in ways that were once unimaginable.
I've always been fascinated by the wave-particle duality of light. Can you explain that in more detail?
Sure. It's one of the key concepts in quantum mechanics. Basically, it says that light can exhibit both wave-like and particle-like behavior, depending on how we observe it.
That seems like a contradiction. How can light be both a wave and a particle at the same time?
Well, it's not really a contradiction. It's just that the behavior of light depends on the context in which we observe it. When we observe light in certain experiments, such as the double-slit experiment, it behaves like a wave. But in other experiments, such as the photoelectric effect, it behaves like a particle.
So how do we reconcile these seemingly contradictory behaviors?
It's all about the concept of wave-particle duality. Light, and indeed all particles at the quantum level, can exhibit both wave-like and particle-like behavior. The key is to understand that these are complementary descriptions of the same underlying reality.
As I see. And how does this relate to the electromagnetic spectrum?
Well, the electromagnetic spectrum is a range of frequencies of electromagnetic radiation, which includes light. Different frequencies correspond to different wavelengths, and the behavior of light depends on its wavelength. When the wavelength is large, light behaves more like a wave, and when the wavelength is small, it behaves more like a particle.
That's fascinating. It seems like there's so much we still don't understand about the behavior of light and particles at the quantum level.
Yes, that's true. But the wave-particle duality of light is one of the fundamental concepts that allows us to make sense of the strange and complex world of quantum mechanics.
Another concept in quantum mechanics that I find fascinating is quantum entanglement. Can you explain that in more detail?
Certainly. Quantum entanglement occurs when two particles are linked in such a way that the state of one particle is correlated with the state of the other, no matter how far apart they are.
That sounds incredible. How does it work?
It's all based on the concept of superposition. When two particles are entangled, they exist in a superposition of states, and measuring one particle affects the other particle, even if they are separated by large distances.
That seems to violate the principle of locality. How can a measurement on one particle affect another particle that's far away?
That's what I thought too. I was skeptical of quantum entanglement for a long time, but experiments have shown that it's a real phenomenon.
So, what are the implications of quantum entanglement?
Well, one of the most interesting implications is that it allows for secure communication over long distances. If two particles are entangled, we can use them to encode information and transmit it over long distances without fear of interception or eavesdropping.
That's amazing. It seems like there's so much we still don't know about the behavior of particles at the quantum level.
Yes, that's true. But quantum entanglement is one of the most intriguing and mysterious phenomena in all of physics, and it holds the potential for all sorts of new technologies and discoveries.
Another topic I've been curious about is the Copenhagen interpretation of quantum mechanics. Can you explain what that is?
Of course. The Copenhagen interpretation is one of the most widely accepted interpretations of quantum mechanics. It was first proposed by Niels Bohr and Werner Heisenberg in the 1920s.
And what does it say?
Essentially, the Copenhagen interpretation says that particles at the quantum level don't have well-defined properties until they are measured or observed.
So before they are measured, they don't exist in any particular state?
That's one way to think about it. According to the Copenhagen interpretation, particles at the quantum level exist in a state of superposition, meaning that they exist in all possible states simultaneously until they are observed or measured. And when they are measured, the act of observation causes the superposition to collapse into a single state.
That sounds very strange. It's hard to imagine particles existing in all possible states at once.
Yes, it's a very counterintuitive concept, but it's backed up by a lot of experimental evidence. And the Copenhagen interpretation has been incredibly successful in making accurate predictions about the behavior of particles at the quantum level.
But doesn't the Copenhagen interpretation lead to some strange paradoxes and contradictions?
Yes, there are some paradoxes that arise from the Copenhagen interpretation, such as the famous Schrödinger's cat paradox. But there are other interpretations of quantum mechanics that attempt to resolve these paradoxes, such as the many worlds interpretation.
It's all so fascinating and mysterious. There's still so much we don't understand about the behavior of particles at the quantum level.
Yes, that's true. But the Copenhagen interpretation of quantum mechanics is one of the most important and influential ideas in all of physics, and it continues to shape our understanding of the universe today.
You mentioned the many worlds interpretation earlier. Can you explain what that is?
Certainly. The many worlds interpretation is an alternative interpretation of quantum mechanics that was first proposed by physicist Hugh Everett in the 1950s. It offers a different way of understanding the strange behavior of particles at the quantum level.
How does it differ from the Copenhagen interpretation?
The many worlds interpretation says that when a particle is measured or observed, the universe actually splits into multiple parallel universes, each corresponding to a different possible outcome of the measurement. In each of these parallel universes, the particle has a definite state, and the observer sees a definite outcome.
The observer sees a different outcome, but they aren't aware of the other universes?
Yes, that's right. The observer only experiences one of the possible outcomes, but in reality there are many different versions of the observer in different parallel universes, each experiencing a different outcome.
That's a mind-bending idea. But does it actually make sense from a scientific standpoint?
Well, the many worlds interpretation is still somewhat controversial, and there are some physicists who don't accept it. But it does offer a way of resolving some of the paradoxes and inconsistencies that arise from the Copenhagen interpretation.
It certainly raises some interesting questions about the nature of reality and our place in the universe.
Yes, it does. And that's what makes the study of quantum mechanics so fascinating and important. It challenges our preconceived notions about the nature of the universe and forces us to rethink some of our most fundamental assumptions.
Let's talk about some of the practical applications of quantum mechanics. How is our understanding of quantum mechanics being used in technology today?
Well, one example is quantum computing. By exploiting the unique properties of quantum systems, researchers have been able to develop computers that can perform certain types of calculations much more quickly than classical computers.
I've heard about quantum computers, but I don't know much about how they work. Can you explain it to me?
Sure. Classical computers use bits, which can be in either a 0 or 1 state, but quantum computers use quantum bits or qubits, which can be in a superposition of states. This means that a qubit can represent both a 0 and a 1 at the same time.
That sounds like it could be incredibly powerful. What are some of the other potential applications of quantum mechanics?
Another area where quantum mechanics is being applied is in cryptography. Quantum key distribution, for example, uses the principles of quantum mechanics to create unbreakable codes that are immune to hacking.
That could be incredibly important for keeping sensitive information secure. Are there any other areas where quantum mechanics is being used?
Yes, another area where quantum mechanics is being applied is in sensing and imaging. By using the properties of quantum systems, researchers have been able to develop sensors that are much more sensitive than classical sensors. This has applications in everything from medical imaging to environmental monitoring.
It's incredible to think about how our understanding of quantum mechanics is being applied in so many different areas. It really shows how important it is to continue to study and understand this fascinating field.
Another important application of quantum mechanics is the confirmation of particle-like behavior of light through the photoelectric effect.
Could you explain that in more detail?
Sure. The photoelectric effect is when photons of light interact with electrons in a metal, causing the electrons to be emitted. According to classical physics, the energy of the light should be proportional to the number of electrons emitted. But experimental data showed that this was not the case.
What did quantum mechanics reveal about this phenomenon?
Well, the explanation came from the idea that light is made up of particles called photons, each with a discrete amount of energy. When a photon is absorbed by an electron in the metal, the electron gains the energy of the photon and can escape the metal's surface. This explains why the energy of the light does not determine the number of electrons emitted.
That's fascinating. So, quantum mechanics revealed that light has both wave-like and particle-like behavior?
Exactly. The photoelectric effect demonstrated the particle-like behavior of light, while other experiments, such as the double-slit experiment, showed the wave-like behavior of light.
It's amazing how our understanding of light has evolved over time. What other insights has quantum mechanics revealed about the behavior of light?
Well, another important insight is that light can be both a particle and a wave at the same time, depending on how it is observed. This is known as wave-particle duality.
It sounds like quantum mechanics has completely transformed our understanding of light and its behavior.
Absolutely, and it continues to do so with new experiments and discoveries being made all the time. Speaking of wave-particle duality, there's also an interesting phenomenon called the Compton Effect that confirms the wave-like behavior of particles.
The Compton Effect? What's that?
It's when a photon of light collides with a particle, like an electron, and is scattered off in a different direction. The wavelength of the scattered light is longer than the original wavelength, which is known as the Compton shift.
How does this confirm wave-like behavior?
Well, the scattered photon behaves like a wave, with its wavelength and frequency determined by its momentum, and since it's interacting with a particle like an electron, it also exhibits particle-like behavior.
So the Compton effect demonstrates both wave-like and particle-like behavior of matter?
Exactly. It's another example of wave-particle duality in action, and it's not just limited to light and particles, but can be observed in other physical systems as well.
It's remarkable how much quantum mechanics has expanded our understanding of the behavior of matter and energy.
Indeed, and there's still so much more to learn and discover. That's what makes science so exciting, wouldn't you agree?
Speaking of wave-particle duality, I've heard of the famous double-slit experiment which demonstrates the duality of matter. Can you explain it to me, Albert, and what does it show?
Sure thing, Nikola. The double-slit experiment involves firing a beam of particles, such as electrons, at a barrier with 2 slits in it, and then observing the pattern of the particles that pass through the slits on a screen behind the barrier.
But if the particles are being fired individually, how can they be creating an interference pattern like waves?
Well, when the particles are fired one at a time, they create an interference pattern on the screen that is characteristic of waves, even though the particles are being fired individually.
So the particles are behaving like waves and exhibiting wave-particle duality.
That's the interesting part. The particles are behaving like waves and interfering with each other as they pass through the slits. It's as if each particle is going through both slits at the same time and interfering with itself.
It's incredible to think that even particles that we think of as discrete entities can behave like waves.
Exactly. And this experiment has been done with not only electrons, but also with atoms, molecules, and even large molecules like buckyballs. It's a fundamental property of the universe, and it's something that quantum mechanics helps us understand.
Another important aspect of quantum mechanics is the uncertainty principle, which states that the more precisely you know the position of a particle, the less precisely you can know its momentum, and vice versa.
Yes, I've heard of the uncertainty principle, but has it been experimentally confirmed?
Absolutely. One famous experiment that confirms the uncertainty principle is the Heisenberg microscope experiment. In this experiment, a beam of electrons is directed at a target with a hole in it. The electrons passing through the hole are then focused by a microscope, and their positions are measured with high precision.
And what did they find?
They found that the measurement of the position of the electrons caused a disturbance in their momentum. This disturbance was greater than the uncertainty in momentum predicted by the uncertainty principle.
So, the experiment showed that the uncertainty principle is a fundamental property of the universe.
Exactly. And the uncertainty principle has been confirmed in many other experiments as well. For example, the Stern-Gerlach experiment showed that the measurement of the spin of an electron along one axis disturbs its spin along another axis.
It's fascinating to see how the principles of quantum mechanics have been confirmed through experimentation.
Yes, and the confirmation of these principles has led to the development of many practical applications, such as quantum computing and cryptography.
Another phenomenon that I find fascinating is quantum tunneling. Can you explain it to me, Albert?
Certainly. Quantum tunneling is when a particle passes through a potential barrier even though it does not have enough energy to overcome it according to classical physics.
That sounds impossible.
It would seem so, but in quantum mechanics, particles are described by wave functions, which allow them to exist in regions of space where their classical energy would be insufficient to overcome a potential barrier.
So does this mean that a particle can tunnel through any barrier?
Not exactly. The probability of tunneling through a barrier decreases exponentially with the width and height of the barrier. However, the phenomenon is still observable in many physical systems, such as in nuclear fusion and quantum tunneling microscopes.
That's amazing. So the particle can tunnel through the barrier even though it doesn't have enough energy to cross it?
Yes, and this phenomenon has important applications in various fields, such as in the design of semiconductor devices and in nuclear physics.
It's incredible to think that something that seems impossible in classical physics is a fundamental aspect of the quantum world.
Yes, that's the beauty of quantum mechanics. It allows us to understand and predict the behavior of particles and systems that classical physics cannot explain.